All right, so we're going to talk today. We're in section 9.9. How we want to come up with ways of representing functions with power series. We've done a little bit of this. We talked about coming up with a Taylor polynomial representation of a function, and if we can find, we did yesterday. We came up with a general expression for the nth term of the Taylor polynomial that we found, and represented that as an infinite series. So that's one way we can represent functions with power series, is look at a Taylor polynomial and try to find a general expression. But there are some other nice tricks that we can do with series that let us come up with series representations that lead to some nice things. So a couple of properties of power series. We can differentiate and integrate power series on their interval of convergence. So power series are integrable and differentiable. Integrable, yep. So we can differentiate and integrate on their interval of convergence. And because they're differentiable, what else does that guarantee about the power series? They're continuous. So integrable, differentiable, and continuous. So I'm just going to put continuous in parentheses. And that's one nice thing about working with polynomials. You know, polynomials are continuous. So all of these properties are true on their interval of convergence. The result that we get from differentiating or integrating will have the same radius of convergence. As the original. So our result's going to have the same radius, but the endpoints, we have to test the endpoints independently. The endpoints may be different, but they have the same radius. They may have different convergence on their endpoints. I'm going to say endpoints need testing. So just like our original power series, the endpoints converge or diverge independently of what happens on the interior of the radius of convergence. So we can do these manipulations with power series by differentiating them and integrating, and we will take advantage of that today. We can also perform some other operations with power series. So if we have a power series, we can do some other operations with it that often will yield another useful power series. So is everyone good with what we have here? Okay. So our operations. So we're going to say that we have two power series. So f of x is given by one power series, a sub n x to the n, and g of x is the sum b sub n x to the n. And it's the same if we're expanding about a point other than 0. Same concept. We can multiply x by a constant, so f of kx equals the sum of a sub n, k to the n, x to the n. And k is just a real constant. So we can multiply by a constant, and our power series representation would be given by this expression. We can raise our variable to an exponent, and we get raising our variable to exponent in our power series. And we can add power series together. So f of x plus g of x is going to be the sum of a sub n, and I'm going to say plus or minus, I'll put a plus or minus there, b sub n, x to the n. So we can add these two things together. And we're going to take advantage of these operations to manipulate our power series. So questions on our tools, what we're going to use today. Now, one of the most useful kinds, or I'm going to say one of the more useful kinds of power series that we can generate are geometric power series. And these are nice, very nice to work with. Why would we want to work with geometric power series? What are desirable things about geometric power series? What kinds of things do we know about geometric series? They're nice. We know the sum. We know a formula for the sum. So geometric power series, we know a formula for the sum. So we know if it converges, we have this formula for a sum. That makes it very nice to work with. And we're going to rely on that as we manipulate some of these power series. What else makes geometric series nice to work with? What kind of tests do we have to do to determine convergence? How do we know when a geometric series converges?
R is less than 1.
So all we need to know is the absolute value of r is less than 1. Tells us our radius of convergence. That gives us our interval of convergence. So this is all we have to do to come up with our interval of convergence is whatever our common ratio is. We just have to say the absolute value of that thing is less than 1. And we're done. That's where it converges. So these are the things that make geometric power series nice. Now our formula for the sum of a geometric series. A over 1 minus r. So that's our formula. So what we're going to do is if we have some function, expression for a function, we're going to try to manipulate it into this form so we can pick out A and we can pick out R, and then we can determine our interval of convergence, and then we can write this function as a power series. So let's take a look at an example of this, of generating a geometric power series. So we want to find a power series for 1 over x, and we're going to be centered at 1. So what we want to do here, when we're asked to find a geometric power series, we want f of x we want to write f of x, this function, in the form a over 1 minus r, and we want the series is going to be in terms of x minus 1, because we're centered at 1. So we want our series in terms of x minus 1. So what I'm going to do is I'm going to write this so that we have 1 over 1 minus something that has to do with x minus 1. So I'm going to write 1 over x, and I'm going to say that that equals 1 over 1 minus, and I want just this, I want this quantity to be x in the denominator, but I want this x minus 1, so it has to be 1 minus something to do with x minus 1. So I want to write it in some form like this. So what do I have to, what kind of manipulation do I have to do here to get this denominator just to equal x? What do I have right now? I have a minus x in the denominator, right? So I need a positive x. So I know that's going to have to be, my x is going to have to be negative. And now I have 1, and I have a positive 1 here, and I'm 1 minus 1. So doesn't that just leave me with x in the denominator? So this, if I add this all together, I just end up with x. So what I want to do is rewrite this denominator in terms of this thing so that I just end up with the original. So I can write the denominator like this. So this is the sum of a geometric series where a equals 1 and r equals negative x minus 1. So this is our formula for the sum of the geometric series where a equals 1 and r equals negative x minus 1. So I can say 1 over x equals the sum n equals 0 to infinity. A is just 1, so I can put a 1 out here for my a, minus x minus 1 to the n. And I can rewrite this, sum n equals 0 to infinity. Don't have to worry about this 1. I can take this negative 1 to the n out and write it out here. Negative 1 to the n times x minus 1 to the n. And if I write out some terms, this is going to be 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed plus dot dot dot. And this series will converge when the absolute value of x minus 1 is less than 1. So our interval of convergence is going to be 0, 2. So we've manipulated this function into the form of the sum of a geometric series, and that allowed us to rewrite this 1 over x as this power series. So when the question is asking you to write a function as a geometric power series, that's what they're asking you to do. Manipulate your function into the form of the sum of a geometric series. That lets you pick out the a, and that lets you pick out your r. Tells you the interval of convergence, and then you can write out your power series. So now we have 1 over x equals this power series on the interval 0 to 2. Questions on that example? All right, let's look at another one like that. And then we're going to come back to this one. And we're going to work with this one. All right, so we want power series. To represent f of x equals 1 over 2 minus x. So this doesn't tell us where we have to be centered. This doesn't give us a center, so our easiest center is 0. So we're just going to center this at x equals 0 because we're not specifying. So I'm trying to manipulate 1 over 2 minus x into the form. We want the form 1 over, a over 1 minus r. We want it in that form. Well, it's pretty close already, right? I just need to turn this 2 into a 1. So what can I do to turn that 2 into a 1? What's that? So if I where are you talking about multiplying?
On the top. Oh wait, no, that wouldn't work out.
Right. So let's divide everything by 2. So I'm going to say 1/2, dividing everything by 2, over 1 minus x over 2. Now we have our form. This is a, and r is x over 2. A equals 1/2, r equals x over 2. So I can write f of x equals 1/2. I'm just going to bring the 1/2 out front. 0 to infinity of x over 2 to the n. I could also write this as n equals 0 to infinity. I can bring this 2 inside, so I'd have x over x to the n over 2 to the n plus 1. So that plus 1 accounts for this extra 2. And this is going to converge our radius of convergence. This is when x over 2, the absolute value of x over 2, is less than 1. So when the absolute value of x is less than 2. Make sense? So this is one way we can generate a power series, if we can write our function as in the form of the sum of a geometric series. Then we can pick out our radius, our common ratio, and we can pick out our first term so that we can write this as a geometric series. So that's one way to generate a geometric series. Now what I want to do next is talk about how we manipulate these power series. I want to look back at this series we generated for 1 over x. We came up with this series for 1 over x centered at 1. We're going to use this to generate a power series for the natural log of x centered at 1. So now we want to find a power series for natural log of x centered at 1. Well, we know that the natural log of x equals the integral of 1 over x dx. And we just generated a power series for 1 over x, centered at x equals 1. So I'm going to say that the natural log of x equals the integral of the sum n equals 0 to infinity, the series that we just generated for 1 over x, of minus 1 to the n x minus 1 to the n dx. One thing that we have to be careful with when we work with integrals of power series is we need to explicitly account for this constant. Because this constant, we could have this constant, so because we're performing an indefinite integral, we have to account for that constant. And we're going to figure out the constant by plugging in a known value for x and the natural log of x. And that will give us the value of this constant. So we have to account for this. All right, so let's do this integration. So this is, I'm going to write this, I'm going to put my c out front so I remember to keep it there. And plus, I don't have to worry about the summation. I can bring the summation out. I can bring the negative 1 to the n out. So that's not going to change when we integrate. Integral of x to the x minus 1 to the n dx. So what is the integral of x minus 1 to the n dx? N is just my exponent. N is just a number. So we have x minus 1 to some power. What's the integral of x minus 1 to some power? Our new exponent is n plus 1. And then I need to account for that. So what do I have to do with that n plus 1? Put it on the bottom. So there's my power series for natural log of x centered at 1. But I need to account for this constant. So I'm going to say when x equals 1, this sum is going to be what? 0. And the natural log of 1 is, we know, is 0. So we have c equals 0. So we plug in x equals 1. We know the natural log of 1 is 0, so c equals 0 in this case. So we don't have, so this constant turned out to be 0. So we finally have, by taking this integral, the natural log of x is sum n equals 0 to infinity of x minus 1 to the n plus 1 over n plus 1. And if I write out some terms, x minus 1 over 1. Oh, and I forgot my minus 1 to the n here. I forgot to write that down here. I have that minus 1 to the n there. So my signs alternate, x minus 1 squared over 2 plus x minus 1 cubed over 3 minus dot dot dot. So this would be a power series representation for natural log of x centered at x equals 1. And we know that it converges on the same interval, or it has the same radius of convergence as our series for 1 over x. And we can test the endpoints and see that our interval is 0, 2. So this would be a power series representation for the natural log of x centered at 1 for x between 0 and 2. It would converge for x between 0 and 2. And we found this by taking this integral. We integrated a known power series. So questions on what we did there? Trying to make this look a little neat. So, question? Okay. And didn't we generate a Taylor series approximation for 1 over x the other day? For natural log of x? Centered at 1? Did we do that as an example? I think we did. So just a different approach to generating power series. Integrating, differentiating known power series, great way to generate other power series. So we went from a power series for 1 over x to a power series for natural log of x. So nice tool. I want to look at one more, and this one's my favorite. This is my favorite thing that we do in power series is this next example. We want to find a power series for f of x equals inverse tangent of x. So think about generating Taylor polynomials for inverse tangent of x. Think how tedious that would be. So to generate Taylor polynomials, we have to do a bunch of derivatives of our function. So what's a derivative of the inverse tangent of x? 1 over 1 plus x squared. So that would be my first derivative. To generate more polynomials, I would take the derivative of this thing. Then I would have to take the derivative of that. So we have this quotient. So that makes things complicated. It would be fairly tedious to generate a Taylor polynomial for inverse tangent of x. Doable, but kind of tedious. Let's use this. What does this look like? Sort of. Like the sum of a geometric series. This looks like the sum of a geometric series. So let's play with this a little bit. We're going to look at g of x equals 1 over 1 plus x. Because one of my properties of power series was if we figure out a power series, we can then raise each term to an exponent to generate a new power series. So let's just look at this one. I'm going to rewrite this as 1 over 1 minus x. There's the sum of a geometric series. A equals 1 and r equals negative x. So I can write 1 over x as a power series. Or sorry, 1 over 1 plus x equals the sum, n equals 0 to infinity, of minus x to the n. And I'm going to rewrite that as n equals 0 to infinity of minus 1 to the n, x to the n. And now to get my power series for 1 over 1 plus x squared, I'm just going to substitute x squared in here. So 1 over 1 plus x squared is going to be the sum, n equals 0 to infinity, of minus 1 to the n, x to the 2n. Now how do we get from here to the inverse tangent? We're going to integrate. Now we're going to integrate this. So the inverse tangent equals, and I'm going to put my c out here, we need to explicitly account for that, plus the integral of the sum of n equals 0 to infinity of minus 1 to the n, x to the 2n dx. I don't have to worry about the sum and the minus 1 to the n inside the integral. So when I integrate, I get c plus the sum n equals 0 to infinity. What's the integral of x to the 2n dx? X to the 2n plus 1 divided by 2n plus 1. And, oh, I forgot my negative 1 to the n again. Thank you. Negative 1 to the n. Got to put that in there. We need this to alternate signs to work. And then we're going to substitute in a nice quantity. So when x equals 0, so I substitute x equals 0 in here and I get 0. The inverse tangent of 0 is what angle produces a tangent of 0? 0. So when x equals 0, that tells us I get 0 equals c plus 0, so c equals 0. Doesn't always turn out that way, but in this case, in the last two cases, it did. So we have the inverse tangent equals the sum n equals 0 to infinity of minus 1 to the n, I won't forget it this time, x to the 2n plus 1 over 2n plus 1. And if I write out a few terms, x minus x to the third over 3 plus x to the fifth over 5 minus x to the seventh over 7 plus dot dot dot. And here's a really cool thing that comes out of this. Inverse tangent of 1. What's the inverse tangent of 1? What angle gives us a tangent of 1? 45 or pi over 4? Pi over 4 equals this gives us an infinite sum that sums to pi over 4. Kind of a cool thing. So questions on what we did there? When you can work with power series this way, when you can think about differentiating, integrating to get to other series that you want, that's a great tool to have to be able to use these power series and work with them this way. This power series can help you, just some applications, help you evaluate difficult integrals. So if you have an integral you don't know how to evaluate, if you can find a power series expansion or power series expression for your function, that might make your function more easy to integrate. Computation, power series are much easier. Computers understand doing things like this. And power series also let us approximate impossible integrals. There are some functions that we cannot integrate using elementary functions. Power series let us approximate those integrals. Last thing I want to do is just write down a list of common power series. These, I'm not going to test on these specifically. These are just good ones to know in general. Kind of like the limit that produces E. Some of these power series are good just to realize, oh, is that the power series for such and such? 1 over 1 minus x. And over here I'm going to put our radius of convergence. E to the x, we talked about that one. Cosine of x, similar. Sine x gives us odd powers, cosine x gives us even powers. We just talked about the inverse tangent of x, and we also produced a, let me write here, natural log of x plus 1. And we just came up with one for inverse tangent of x. And I forgot to write our inverse tangent of x converges on our interval is -1 to 1 for inverse tangent of x. So those are some common power series. E to the x and sine and cosine. You'll see a lot. The inverse tangent you'll see a fair amount, but these three are really the big ones that you'll see very frequently. All right, questions? We're down to the wire today. Okay, homework. Prepare for your test, plus okay, there you go.